Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Pada kesempatan kali ini, saya Salma Meldiyana beserta rekan-rekan saya ada Imaniar Salsa, Rayhan Zharfan, dan yang terakhir ada Rifqi Yuner akan membuat sebuah video reaction tentang Newton Interpolation dan Lagrang Interpolation. Nah, untuk videonya sendiri ini dari University of South Florida yang diampu oleh Profesor Autarka. Ya, baik, langsung saja kita mulai videonya.
In this segment, we will talk about Newton's divided difference polynomial, method to do interpolation, so we'll go ahead and get started with the linear interpolation to see that how Newton's divided difference polynomial interpolation is done when we have linear interpolation. So the way we're going to present the problems are chosen x naught, y naught, x1, y1, find the linear Newton's divided difference polynomial. So we're going to use a contraction here or a abbreviation here, NDDP here. So let's go ahead and see that how linear interpolation is done by using Newton's divided difference polynomial. Now some people might say, hey, what does this mean, chosen? The reason why we're talking about chosen is because we may be given a lot of points, but when we are doing linear interpolation, we only choose 2 points. And we'll leave it so far as how we choose those 2 points. Once somebody gives us, let's suppose, 100 data points, we'll leave that up to an example and show you that how we're going to choose those points. Again, we are given these points, so basically what we are given is y as a function of x, but we are given y at only 2 points, that is at x naught and x1. So it's a discrete function. So many times you'll find out that we'll be using like y naught and f of x naught interchangeably. They mean the same thing. Same thing for y sub 1, we'll use interchangeably with f of x1. Because basically the problem is that you are given your function of x, your y is a function of x, and that function is given at, let's suppose, certain number of data points. So these are interchangeable when we talk about Newton's divided difference polynomial or any other polynomial interpolation. So let's go and see that how this method works. Is that if you go back and look at direct method, you would have chosen the linear interpolant to be y is equal to a naught plus a1x. That is the interpolant which you would have chosen. So in that case, what happens is that you have a naught and a1. These are the 2 coefficients of the linear interpolant which you have to find. And you set up 2 equations, 2 unknowns, by basically saying that, hey, this particular value of at x equal to x naught, the value is y naught. So let me just go ahead and write it down. You would have done this, and you have y1 equal to a naught plus a1 times x1. So that's what you have done. You would have set up 2 equations, 2 unknowns, solved for a naught and a1, and there is your linear interpolant. But in the Newton's divided difference polynomial method, it's we're still using a first order polynomial, but it is used in a different form, and the form looks like this. We have f sub 1 of x. This f sub 1 stands for the first order polynomial, is given by the form like this. So we are choosing the form to be still a linear interpolant, but the form is chosen to be b naught plus b1 times x minus x naught. You still have the 2 unknowns b naught and b1. And the reason why I showed you the direct method right here is so that you can develop an appreciation for why Newton's divided difference polynomial, although it's going to give us the same polynomial as the direct method or any other method, why does it become attractive? And you'll see that in a little bit. So let's go and see that how we're going to find b naught and b1. So we know that the value of the function, at x naught is same as the value of the function at x naught, which is same as y naught, will be equal to b naught plus b1 times x naught minus x naught. So all I'm doing is substituting the value of x equal to x naught in there. And I'm saying that, hey, I know that the value of the function at x naught, which is the function f of x naught or y of naught, you may call it. So I know that, so I get f of x naught is equal to just b naught, because this is going to become 0. Same thing, I know that this first order polynomial which I have at x1 will be equal to the value of the function at x1 which is given to me, which is the same as the value of y of 1, will be equal to b naught plus b1 times x1 minus x naught. And then since I know, so this is f of x1, since I know that b naught is f of x naught, I'm going to just substitute, because I just found out what the value of b naught is. I'm going to substitute it back in here, plus b1 times x1 minus x naught. And this gives me b sub 1 is equal to the value of the function at x1 minus the value of the function x naught divided by x1 minus x naught. So what you're finding out is that I'm able to find out the value of b sub 1 also by simply subtracting the values of the function at the 2 points that are given to me divided by the difference between the two x values which are given to me. So what you're finding out, which is different from what we have in the direct method, is that the values of the unknown coefficients b naught and b1, which you're finding them here, are found without having to solve two simultaneous linear equations. We're still solving two equations, but they don't have to be solved simultaneously. So that's the beauty of Newton's divide difference polynomial method, that the coefficients of the polynomial are obtained by just solving one equation at a time. So as opposed to direct method where you will have solved two simultaneous linear equations, hence use some numerical methods such as Gauss elimination or eddy decomposition to find out what the unknown coefficients of the polynomial are. So based on this, what we have is that our first order polynomial, which we have used to approximate our function from x naught to x1, is given by this, where b naught is nothing but the value of the function at x naught, and b1 is nothing but the value of the function is the slope between x1 and x naught, the straight line slope between those 2 points, and is given by that. So what you're finding out is that it is simply given by the value of the function at the first point and the value of the slope between the first derivative slope between x naught and x1. This one is written as f of x naught, so this is called the 0th divided difference, and I can write this as f of x1 comma x naught. So this is called the first divided difference, and that's why it's called the divided difference method, because you are using divided difference approximations for the slope and for the function itself. This will be called the 0th divided difference. Now, this may not make too much sense right now, but once we talk about second order interpolation and general order interpolation, you will see what the significance of rewriting these unknown coefficients in this particular form is. So this is basically the definition of the first divided difference is just exactly this. The definition of the 0 divided difference is exactly this. So there's nothing more to explain there, but it's just a rewriting of our coefficients of b naught and b1. And in the next segment, we'll take an example, but this is the end of this segment.
Berarti B0 itu selalu fungsi sebelumnya gitu ya? B0 itu selalu sama dengan fx0 atau fx sebelumnya?
B0 sama dengan fx0.
Berarti namanya selalu 0.
fx0.
Tadi kan fx0 kan 0 kan hasilnya?
Untuk fx0 sama dengan B0.
Enggak, tadi yang hasil fx0 nya?
Enggak bakal.
fx0 sama dengan B0.
Yang kamu maksud dicoret ini nih, dicoret.
Itu
sama dengan B0.
Oh, B0 doang.
Iya.
B0 nya tapi kita tahu ini dari mana?
Dari x0.
Jadi ada fungsi.
Oh,
jadi
YT
kan ada fungsi Y sama dengan,
berarti nilai B0 itu x0.
Enggak, jadi kayak gini. Ya kan ada persamaan linear. Ya. Persamaan linear itu kayak Y sama dengan AX ditambah B.
Ya.
Ya, jadi atau enggak Y sama dengan 4X ditambah 2 misalnya. Nah, yang B0 di sini teh 2. Nilainya. B1 yang di sini teh 4, kan 4X tambah 2. 2T sama dengan B0, 4T sama dengan yang B1 gitu.
B0 tuh hasil dari substitusi X0 gitu maksudnya. Ya nggak sih?
B0 teh hasil dari substitusi.
Dari X0. Kan ada persamaan tuh.
Ya.
Kita masukin X0. Nah, jadi B0. Ya nggak sih? Substitusi.
Maksudnya apa? Angin deh.
Nilai si X0 tuh dimasukin ke persamaan yang kamu maksud tadi.
Oh enggak, jadi ini mah belum masukin ke persamaan. Jadi kan misalnya ada fungsi Y. Fungsi Y sama dengan fx kan?
Iya.
Nah, jadi Y sama dengan 4x. Misalnya ini contoh.
Iya, oke.
4x ditambah 2. Nah, B0 di sini teh 2, B1 di sini teh 4. Jadi X di sini teh X dikurangi X0. Jadi ini teh sebenarnya NDDP ini teh sama aja kayak yang di metode.
Oh.
Kalau yang di metode mah kan udah pasti diketahui, misalnya kayak 4x dikurangi 2
Ya.
sama
B0 sama gitu ya.
Ya, misalnya kan Y1 teh 4x dikurangi 2, Y2 teh 5x dikurangi 3 misalnya.
Ya.
Jadi kan kita bisa nentuin x-nya. Nah, tapi kalau yang di bagian sini teh yang B0 sama B1-nya teh nggak diketahui gitu.
Oh, I see. Oke. Copy.
Jadi nyarinya teh pakai
Kita tetap harus
yang NDDP. Kalau yang di metode mah kan udah diketahui. Ya, sama yang itunya. Kalau yang ini mah belum.
Ngerti.
Berarti lanjut dia nih.
Oke, kita lanjut ke video selanjutnya.
Managing your projects shouldn't feel like this.
Oke, ini example-nya ya.
Iya.
Oke.
In this segment, we're going to take an example for the Newton's divide difference polynomial method, and we're going to take the example for linear interpolation. So how do we do linear interpolation? By using Newton's divide difference polynomial method. So let's suppose this is the example. So somebody is giving you velocity as a function of time. Time is given in seconds, velocity is given in meters per second for this rocket. The upward velocity is given to you. It's given as 0, 0, 10, 362.78 at 15. At 20 it is 517.35. At 22.5 it is 602.97. And at 30 it is 901.67. So these are the numbers which are given to us, and we are asked to do linear interpolation based on the fact that we want to find what the value of the velocity 16 is. So we want to use linear interpolation, we want to use Newton's divide difference polynomial method. We're given 6 data points, and we want to find out what the value of the velocity at 16 seconds is. So again, as we were talking about when we were deriving Newton's divide difference polynomial, we talked about that, hey, rather than posing the problem as given 2 data points, do the linear interpolation, we say chosen 2 data points, because in most cases, you won't just have 2 data points, but you'll have a number of data points. So you have to come up with a scheme to choose it. For linear interpolation, it's pretty simple, because all you have to do is to figure out that the point at which you are interested in finding out the intermediate value, that the numbers have to be between, that the number has to be between the 2 data points, so and closest to them. So 16, it is between 15 and 20, and it is also at the same time, these are the 2 closest t values which you have. So that's why we're choosing 15 and 20. We're not choosing 10 and 20, for example, because 15 is closer to 16 than 10 is. So it's pretty straightforward. So you have to find out the immediate bracket, immediate 2 data values which bracket your value to the last 16. I also want to emphasize that these data points which are given to you here, although we are giving them in an ascending order so far as the time is concerned, going from 0 to 30, for Newton's divide difference polynomial method or direct method or Lagrangian interpolation, it is not required for these data points to be in any kind of ascending or descending order. So it's extremely important to realize that. A lot of people think that that is the case. You do have to put them in ascending order if you were doing something called spline interpolation. So let's go and see that how we're going to apply Newton's divide difference polynomial method to this particular problem. So we know that the velocity v sub 1t, which is standing for the first order polynomial, will be like the formula v0 plus b1 times t minus t1, where b naught is the value of the function at the first data point, and b1 is the slope between the two data points of t naught and t1. So we get this. So in our case, what we have is that, so let's go and write down what t naught is. T naught is 15. The value of the velocity at t naught, which is one of the data points given to us, is 362.78 meters per second. The value of the velocity at 20 is given to us, that's v sub t1, is given to us as 517.35 meters per second. So based on this information which we already have, we should be able to find b naught and b1. So b naught is nothing but the value of the velocity of t naught, which is 362.78, which is right here. And b1 is the velocity at t sub 1 minus the velocity of t sub naught divided by t sub 1 minus t sub naught. And this one is equal to v sub t1 is 517.35. The value of the velocity at t naught is 362.78. And we divide it by t sub 1 minus t sub naught, which is, no, this is t sub 1. T sub 1 minus t sub naught, which is 20 minus 15. So based on this, we should be able to find out what b sub 1 is. And we are able to find b sub 1 to be equal to 30.914. So we have the value of b sub 1, we have the value of b sub naught. So we should be able to write down the first order polynomial which we have. And that first order polynomial, again, as we said, is of the form b naught plus b1 times t minus t naught. And b naught is 362.78 plus b sub 1, which is 30.914 times t minus t naught, which is 15. So this is what turns out to be the first order polynomial, which is valid between 15 and 20. So again, I want to emphasize another point is that whenever you're going to write interpolants which you are finding by using any of the methods, that you do give the domain in which that interpolant is valid. So since we have used 15 and 20 as the two data points, that means that that this interpolant which we just found out is valid between the points of time of 15 and 20. However, what we are interested in is finding out what the value of the velocity is, approximate value of velocity is at 16, which we can just obtain by simply substituting 16 in here, 30.914 times 16 minus 15, and this number here turns out to be equal to 393.69 meters per second. So that's our approximation. Now, one of the things which I do want to mention is that this is a first order polynomial. This is the same first order polynomial which you would have obtained by using direct method. So if I expand this particular polynomial, I'll get v sub 1t. If I just expand this by simply multiplying this to this and this to this, I would get minus 100.93 plus 30.914t. And this particular interpolant is the same interpolant which I got by using direct method. So there's no difference because the polynomial has to be unique. So there's no difference between this polynomial which I would have obtained by using direct method and this polynomial right here. Just the form is different. As you saw that the reason why we are writing in this particular form is because calculating the value of b naught and b1 do not require us to solve simultaneous linear equations. And that's the end of this example.
Oke. Ini terus setelah dikasih contoh lebih tercerahkan ya nggak sih?
Ya, benar sih. Jadi kebayang biasanya seperti apa?
Iya. Lebih simpel mungkin yang dikasih dulu kesimpulan dari Rayhan atau Rifqi mungkin. Dari contoh soal yang tadi kelihatan banget nih. Kita harus nentuin range-nya
Yang pasti mah kita nggak tuh yang paling dekat sama yang X kita cari gitu range-nya.
Betul sekali. Jadi cari range.
Jangan cari yang jauh biar enggak terlalu jauh juga itu.
Yang kedua langsung substitusi.
Rumus yang tadi.
Iya, rumus yang tadi nih, Nah, ini substitusi aja. Ya kan tinggal ya
lebih kebayang ya. Udah di sini langsung
ya nyari kebersamaan B0 sama B1, terus masuk
persamaan
masuk substitusi B0 sama B1,
dan akhirnya dapat hasil akhirnya
ini. Nah, itu kan.
Oke. Ternyata lebih simpel ya daripada teorinya tadi. Dengan contoh memang lebih mudah dipahami, lebih kebayang. Oke, lanjut ke video berikutnya. Mau kuadrat atau mau langsung ke Lagrang? Lagrang aja ya. Oke, check this out. Kita keluar dari video ini dulu. Kita ke Lagrang. Oke, di Lagrang juga bakal ada beberapa session yang bakal kita putar ya.
Ada part 1, part 2, lalu ada sama example tadi satu.
Nice.
Langsung ya.
Langsung aja. Apakah akan sama dengan
Rasanya ini bakal lebih susah.
serius?
In this segment, we're going to talk about Lagrangian
Soalnya dia di akhir juga.
interpolation.
Pahamnya pasti di example.
Iya benar.
And I'm just going to show you the theory of Lagrangian interpolation in this segment. We're not going to derive the Lagrangian interpolation in this particular segment, just to show you the formulas of it. So as we know that if somebody gives us a certain number of data points, so let's suppose somebody gives us 4 data points. Then I know that if I'm going to draw some kind of a polynomial through it, it'll be a third order polynomial. So somebody's giving me 1, 2, 3, 4 data points and wants to say that, hey, go ahead and find out the polynomial which goes through those 4 points. It will be a third order polynomial. So it'll be a third order polynomial. Now, we have already talked about in the previous segments how to find this third order polynomial by using something called the direct method and something called the Newton's divided difference method. So those are the two methods we have already talked about how to find this polynomial. So it is the same polynomial whether you are using direct method or Newton's divided difference method, because it has been shown in another segment that if somebody gives you a certain number of specified points where all the x's are different, then the polynomial which goes through those particular points is unique. So many times people say that one should not call it Lagrangian interpolation or Newton's divided difference method interpolation. We should call it that is the form, Lagrangian form of polynomial interpolation. But it doesn't really matter till the time you realize that the polynomial, no matter which method you're going to use, through a certain number of specified points, if you're doing polynomial interpolation through n points, the polynomial which will go through those number of points is unique. So what does Lagrangian interpolation look like? It looks like as follows, that given, let's suppose, n plus 1 data points, so if somebody is giving you n plus 1 data points, like x naught, y naught, x1, y1, all the way up to x of n, y of n. So somebody is giving n plus 1 data points. Of course, we are already saying that all these x naught, x1, x2, all the way up to xn, they are different from each other. In that case, the nth order polynomial, so the Lagrangian form of interpolation or Lagrangian polynomial interpolant, looks like of this form. This n stands for, that's the nth order polynomial. Looks like this summation here, I equal to 0 to n, else of I, let me not write my L like that, let me just write my L as it is in the notes, else of I of x times the value of the function at the x points. So basically what you have is that you have else of I of x, which is a function of x,
Oke, jadi intinya jangan.
So these are the weighting functions basically which you are giving to the values of the function at different values of x, because I is going from 0 to n, so it's basically the values of the function at x naught, x1, x of n. So keep in mind that f of x of I is nothing but y sub I. Okay. So there's no difference between the point at y sub I which is given to you, like y naught, y1, yn. That's the same as the value of the function at x of I. So let's go ahead and see that what this weighting function is. So you have this weighting function L sub I, Li of x. So we want to see what that weighting function Li of x looks like. So I'm going to write it on the board here, so that because I show it in expansion, that's why I'm writing it here. Li of x is written as a product. So the pi symbol stands for the product. For j equal to 0 to n, where n is the number of order of the polynomial, j not equal to I. You're going to find the product of this quantity, x minus xj divided by xi minus xj. That's what you're going to find the product of. So again, keep in mind that it is a function of x, but the other things which are in this product are the values of x themselves at different points. Now, if you are going to expand it, because sometimes people get intimidated by this particular symbol of product, then also we're saying j is not equal to I. So I'm going to show you an expanded view. That way you will have a little bit better understanding of it. Now, first you got to understand this, you have L sub I x here. So this I is going to be same once your I is fixed. So you'll find out that as I start writing the expanded version of this number or this x of I is not going to change, because the product is going, the product lower limit and upper limit is for on j equal to 0 to I. And of course, j is not equal to I. So you'll have x minus x1, x naught, because that's the first value of j it's going to take, times x of I is going to stay same for all of these cases, minus x naught. So this and this number is exactly the same. Then what's going to happen is next time you're going to get x minus x1. You're going to get x1 divided by x of I minus x1. And this is going to continue to take place all the way up to x minus x of I minus 1 divided by x of I minus x of I minus 1. The reason why I went all the way up to that particular term is because j is not equal to I, so I'm just writing the term which is before j equal to I. And the next term, since it says j is not equal to I will have not x minus x of I, but x of I plus 1. That's what I'll have. Divided by x of I minus x of I plus 1. All the way up to the last term, which will be x minus x of n divided by x of I minus x of n. So this is the term which you'll have to calculate as the weighting function for each I, where I is going from 0 to n. So that's how this is going to work out for your for the Lagrangian interpolation. And that is the end of this segment. We'll take some examples in the next. We'll take examples in the next 3 segments, and this is the end of this segment.
The academic year is ramping up. Stay motivated with Check Study Pack and don't miss a thing.
Example linear interpolation. Semoga makin
Jadi yang
kebayang.
itu tadi itu maksudnya apa? Simbol kan bukan
Simbol.
bukan simbol.
Bapak si baru artinya beda.
In this segment, we're going to take an example for Lagrangian interpolation.
Biasanya kalau ada contoh soal lebih simpel sih.
Benar, jadi paham.
Lebih paham.
So the example which we are taking is the simplest example of linear interpolation. So let's suppose somebody is giving you the data like this one.
tadi ya.
They're giving you velocity versus time for a rocket. Time is given in seconds, velocity is given in meters per second. And these are the numbers which they give you, that at time t equals 0, velocity is 0. At 10, it's 227.04. At 15, it is 362.78. At 20, it is 517.35. At 22.5, it is 602.97. And at 30, it is 901.67. So the question which is being asked is that you are given this data here. So given this data here, you are asked to find the value of the velocity at 16. So we know that since we are given 6 data points, but we are only conducting linear interpolation, so that's the part of the example statement that you need to conduct linear interpolation. We're going to choose the two closest points which are to 16, which seem to be 15 and 20. But at the same time, they also have to bracket the number 16. So the two numbers which you're going to select for linear interpolation not only have to be closest to the point where you're interested in finding the intermediate value, but also they have to bracket the point itself. So what that means is that we have chosen two data points for our linear interpolation, and we want to conduct this linear interpolation based on the two data points which you have chosen. So I'm going to write those down. I got 15, 20 are the times. The values are 362.78, and the value here is 517.35. Based on this, we already know that the velocity now should look like, so far as the Lagrangian polynomial interpolation is concerned, will be summation I equal to 0 to n L sub I t v sub I t. V of t sub I. So it is the weighting function multiplied by the value of the velocities at the different points which you have chosen. And since n is equal to 1 in this case, because we are choosing a linear interpolant, so it's an order of polynomial 1, we have L sub I t, v of t sub I. And if I expand this, I'm going to get L naught of t times v at t sub naught plus L1 of t times v sub t1. So basically you have two values of the velocity at t naught and t1, and you're giving them a weight of L naught of t here and L1 of t right there. Now what is t naught and t1? This is t naught and this is t sub 1. It won't matter if you switch them. That's something which you do need to understand. And this one here is the value of the velocity at t naught, and this one is the value of the velocity at t sub 1. So we have everything which we need, and all we have to do is to calculate what these individual numbers are for L naught of t and L1 of t. So what I'm going to do is I'm going to write down here L naught of t times the value of the velocity at 15 plus L1 of t times the value of the velocity at 20, because those are the values of t naught and t sub 1. So this gives you L naught of t, v sub 15 is 362.78 plus L1 of t times the value of the velocity at t sub 1 is 517.35. So let's go and find out what these two Lagrangian weight functions are, so that we can complete this particular interpolant here. So the first one is L naught of t. So L naught of t will be equal to the product going from j equal to 0, j naught equal to I, all the way up to n, which is 1 in this case. Okay. Times t minus tj divided by t sub I, which is I is not 0 minus t sub j. So if you look at the original formula which I have, this comes from pi j equal to 0, j naught equal to I going to n is 1, t minus t sub j divided by t sub I minus t sub j. That's where all of this is coming from. And since I is equal to 0, that's why I have 0 here. Since n is equal to 1, linear interpolant, we have a 1 here. So what this means is that we're going to get t minus, when I take j equal to 0, I'm going to get t minus t sub naught divided by t naught minus t sub 1. Okay. Sorry, this will be t sub 1 right here. Because when j is equal to 0, j is not equal to I, so I cannot choose j equal to 0. I cannot choose j equal to 0 because I is equal to 0, so that's why this term is now going to be taken. So when I was saying I'm taking j equal to 0, I cannot take j equal to 0 because I have I equal to 0 there. So the next term will be j equal to 1, so that's why I have t minus t sub 1 and t naught minus t sub 1. Now L1 of t, which is the other weighting function, will be going from, again, j equal to 0 to 1, j not equal to I, t minus t sub j divided by t1 minus t sub j. So the only difference with the previous expression is that now you have instead of 0, you have 1 now, so you're going to 1 here. Now, what you're going to do is you're going to start from j equal to 0, which is not equal to I, because I is 1. So that means that I got to put j equal to 0 here. I get t minus t naught divided by t1 minus t naught. Now I cannot, the next term, which is j equal to 1, is the same as I equal to 1. So that term will not be written there. So we only have a single term there. So that gives us the weight for L sub 1t, and that gives us the weight of L naught sub t. So I'm going to substitute it back into the formula which I had previously. So I had V sub t equal to L naught of t times V of t naught, which was 362.78. 362.78 plus L1 of t times the value of the velocity at 20, which was 517.35. And now I'm going to substitute these weights. So I get t minus t1 divided by t naught minus t1 times 362.78, then plus t minus t naught divided by t1 minus t naught times 517.35. And you will see that now I can substitute these values. I get t minus t1 is 20 divided by t naught, which is 15. t1 is 20 times 362.78 plus t minus t naught, which is 15, divided by t1, which is 20, t naught, which is 15, times 517.35. So that's going to be my my Lagrangian interpolant. If you want to write it in that particular form and maybe give it a little, try to simplify it if you want to. And we value between 15 and 20 because those are the two endpoints which were chosen for this linear interpolant. But we are interested in finding the value of the velocity 16, so we don't need to necessarily simplify this expression to find the value of velocity 16. We can directly substitute 16 into the expression, and we get 16 here. And the number which I get for the interpolant at t equals 16 will be equal to 0.8 times 362.78 plus 0.2 times 517.35. And this number here turns out to be 393.69 meters per second. And that's what it turns out to be the velocity 16 by using Lagrangian interpolation. And that's the end of this segment.
Oke, Nah, ini udah selesai ya. Nah, di sini mungkin ada 1 atau 2 patah kata gitu dari teman-teman sekalian. Mungkin mulai dari aku deh. Soalnya gampang. Oke. Kalau yang bisa saya simpulkan dari kedua metode tadi itu sama-sama menentukan range. Nah, range terdekat dari value yang akan kita cari. Oke deh, dari aku cukup segitu. Iman?
Mungkin dari Rifqi Yuner.
Oke.
Tambahan dari apa aja? Kalau dari aku sih mungkin fungsi hasil yang dikurangkan dari fungsi dua-duanya itu tadi sama aja, tapi rasanya yang lebih mudah dipakai itu tuh menurut saya itu yang Newton. Kalau dari saya ya, nggak tahu kalau teman-teman.
Aku juga setuju sama Rifqi.
Nah.
Newton.
Gimana sama Iman?
Oh enggak.
Karena kalau misalnya aku mungkin lebih mudah gitu kan. Pertama kan ngebayangin dulu itu nyari B. Nah, itu
Nyari B0 sama B1 tuh kayaknya lebih mudah gitu ya dibandingkan yang
lebih mudah.
tadi ya.
Bayang nyari itu tuh selisih dari setiap detiknya.
Tapi sebenarnya sih kalau B0 tadi sama sih, iya sama.
Itu yang lebih kebayang dari fisika.
Coba Rayhan.
Enggak.
Kesimpulan dari aku kan jadi di linear interpolation ada 3 metode. Direct method, Newton divide difference method, sama Lagrang method atau form, Lagrang form. Untuk yang direct method itu bisa kita gunain kalau misalnya sudah diketahui fungsinya. Sedangkan Lagrang sama divide sama NDDP itu digunain kalau fungsinya belum diketahui.
Nggak jelas gitu ya?
Ya, fungsi. Kalau yang atas kan yang direct method mah fungsinya udah diketahui jadi tinggal dikurangi.
Ya.
Tapi kan kalau fungsinya
atau tinggal
diketahui juga,
dimasukin.
misalnya kita mau pakai Newton doang, kita pengen ngapalin Newton doang juga bisa gitu kan ya, dipakai juga.
Newton. Enggak sih, tujuan digunain Newton teh gagal fungsinya belum diketahui, cuma diketahui. Nah, hasil akhirnya sama hasil awal X-nya sama hasil akhir.
Kayak sematikan yang tadi kalau di kasus.
Segitu saja.
Oke, terima kasih rekan-rekan. Ya.
Terima kasih Pak sudah menonton.
Ya, terima kasih Bapak yang udah ngasih tugas Pak Iwan Awaludin. Terima kasih, di sini alhamdulillah kami dapat menyelesaikan tugasnya.
Bersama-sama.
Iya, betul sekali. Terima kasih atas perhatiannya. Mohon maaf apabila ada salah kata karena di sini kami masih belajar. Cukup sekian dari kami. Wabillahi taufiq wal hidayah. Assalamualaikum warahmatullahi wabarakatuh. Terima kasih.
Sampai jumpa.
Sampai jumpa di kelas, Pak.